I'm Jennifer Hasler, and I'm at Georgia Institute of Technology, and I want to talk about our open source tool set that we use to target and design field programmable analog arrays. And we're going to go through this a bit of an introduction of the material, as then we're also going to talk about and show some hardware and hardware demonstrations of this material. Now, when we talk about field programmable analog arrays, there's a long history of this, but when we're particularly using it, we're talking about a structure for these large-scale field programmable analog arrays. These have been used in a number of places and used in a number of embedded structures. These have been used for looking at acoustic classification and a whole range of acoustic classification structures, talking about embedded learning and classification at microwatt level power levels. And the structure is actually composed of multiple analog and digital components, as well as a digital infrastructure, processor core, and all on the remaining programming infrastructure for this element. So there's a lot of possibilities with this particular structure. So you look at a typical one of these FPAs and they have like a half to a million floating gate elements. And you think that's really great and there's a lot of complexity. But at the same time you think there's a lot of complexity. And you think, well, does a designer need to go through and select these items individually, looking up tables and figuring things out? You might sit there and think, well, that feels better than layout, but it feels kind of like writing machine code, which may still be better for analog design and mixed signal design, but it's still a fairly complex thing. So is there anything else? Why, yes, there is. We can actually talk about what is an open source tool that actually enables this FPA development. And in fact, the tools have been developed entirely to try to deal with these questions. And when we look at a chip like this sort of system on chip FPA, like we showed previously, certainly there's a bit of work in knowing how to build the programming infrastructures and the chip itself, but even that becomes something you want to be able to abstract. There's a whole board infrastructure, there's elements for built-in self-test, but then there's a whole infrastructure for the tools that capture and encapsulate all of this in a useful way. And this is what we're talking about for our open source FPAA toolset that we're going to describe. And so it's been the work over many, many years, initially out of necessity, even though in general most people would think that doing these kinds of tools in an analog space is just a very, very difficult situation. So let's talk a little bit further about these ideas. Before getting into the details, I want to show you at least a high level what the tools will look like. We'll demonstrate this in a little bit later on in this presentation. But if you look at the tools, what you see is you have an open source structure. Everything is encapsulated in an Ubuntu 12.04 virtual machine, and then is actually sitting in Scilab and Xcos, which is, if you're not familiar with it, is an open source MATLAB clone. We've used this infrastructure in classes for over 5 years. And the reason for using the structure is that we wanted to start off with analog design being a graphical sort of flow language. So imagine similar to Simulink, and this block in the middle is exactly what we mean by circuit design. This is actually showing a particular Hodgkin-Huxley circuit model and how we would use this. Well, the structure has a few specific things. One is there's a nice little button at the top of the virtual machine, which has a CAD-SIP button, which is the one button you need to hit to load everything. We put everything into a virtual machine because this became the easiest way to distribute it, not just to our collaborators, but to students. And all they had to do was download the structure, hit one button, make sure the USB is working, and they not only could have the simulation tools running, but the hardware running, usually within about a half an hour. And we would have everything up and working. There is also a whole range of examples, and we actually use a number of different example parts, so that way someone starting off may see blocks that look familiar and they can immediately start working with them. As well as having things in the GUI that allow you to talk about choosing designs, compiling designs, programming them, and a number of other very important features as we typically have found to use. We find that GUIs are fairly self-documenting, and therefore that we use these structures. So it becomes one tool framework to simulate, target, and design in this entire structure. And we do actually see the measured output here as well. That was that we would have gotten actually from the output of the chip directly imported through. And what you find is a whole range of action potentials coming out as you would expect. So before digging into the details of the tools, one of the first things that comes to mind is asking questions about whether you can abstract analog structures. And this is actually really fundamental, as you could tell by the fact that we're building blocks all the way through our infrastructure. And these blocks are very, very critical through the entire part. This whole structure is a slightly abstracted view, but this is exactly what correspond to blocks we have in our infrastructure. And for most people just using it, they pick up the blocks and make things work, or occasionally there's one or two issues and they're kind of surprised at this. But what most people, and so that works reasonably well. But what you don't realize when you look at this is that this amplitude detection block, which has a nice print, you double click on, you get a parameter, would actually be compiled by a number of different circuits. The low pass filter is compiled by another circuit. There are components that actually connect to the processor on chip, both on the input and output structure, and then we also will potentially use shift register blocks that are in there. And on top of that, there's other parts. The arbitrary waveform generator involves a microprocessor. The DC voltage block is actually a compiled floating gate circuit, and the C4 block is actually 3 levels deep of compilation. So what looks like a very nice simple structure, like what you saw on the previous slide, you realize very quickly that there is a lot that's being abstracted and the capability of it being abstracted. So this is the flow of our FPAA tool framework. At one level, you see that everything comes out as sort of a Scilab XCOS kind of framework. At a low level, we get out basically a switch list, which that switch list will allow us with our basically targeting scripts and then assembly language that we put on the processor to do the programming basically programs the chip. In the middle, you'll see that we actually utilize VPR, and we actually take VPR and then add and extend a lot of things around it. For example, we have a technology file to explain our chip, but our chip is an analog chip. We needed to shift things. We have extended the file format for BLIF because, after all, BLIF, which has a format like this, we can actually now put transconductance amplifiers in there as part of that block. But basically the way it starts is that there's actually a digital path and an analog path in here. There's a library from XCOS that allows us to go from here down to an analog BLIF compilation. The digital side, we use the VTR part of the tool for that, so we would compile things to Verilog and from Verilog down. And that gives us a netlist and an I/O pad block. From there, that can all get piped into VPR to be able to do the sort of external place and route components, at least of things that are switches. Now, there are some elements that aren't always switches, and so we handle those separately. And so there's kind of a little bit of a sort of data that gets passed through and around that goes into this VPR to switches, which basically says how do we deal with the programming inside cabs and inside related components. From there, from there, there's sort of all the sort of local interconnect routing, handling things, handling what we call macro blocks, which is additional code for sort of custom configuring a particular cab, and then creating the switch addresses and going for there. So what you end up getting is this interesting block that goes from circuits that splits to analog, digital, and assembly, and all pulls together when it's done into what's a switch list, which is just basically a list of XY coordinates of switches and values and parameters related to them. And this is directly what is used for programming. So it allows us to take blocks like OTAs and various digital components and push this all the way into an infrastructure. Now you might think, wait, if I've got netlist and this sort of BLIF and pads, you're thinking, I can almost see a secondary sort of idea where I could take this out, and if I had some standard cells, I bet I could even take this kind of definition and eventually go to something that's hardware. And it's fair to say that that is something we're working on. The sort of initial thoughts and approaches on standard cells is being looked at, and we're continuing ongoing work and likely a tool that we're going to talk about in the future. So at that point, you begin to think, okay, this whole tool set seems to be basically done, but there's one more wrinkle in this, which is that your floating gate elements are not dead weight. And that's because with your floating gate elements in a crossbar, I can actually do things like vector matrix multiplication or other computations right in the routing fabric. And if I do that, that actually makes it a little more complicated at each of these, some of these stages, because now my routing is not simply just routing, but it's also part of the computation. And this is an area where we often have to be very careful what we're putting together there. So I want to talk and show you some of the tools that we have in our structure. What I'm showing you here initially is a picture from my virtual machine, which is an Ubuntu 12.04 virtual machine that is running within my Mac. And I want to be able to walk you through some of the basic steps of how we start the structure up. This would be basically what you would see if you loaded up one of these virtual machines. My background screen is slightly different, but otherwise looks similar. And what basically happens with this open source tools after you download it is that you can pull everything up under CAD-SIP, and it'll eventually load up the various tools that we use for that we're going to be using for our open source toolkit. Now, in this open source toolkit, as it's when it loads up as it sits in Scilab 5.4.1, and all these versions could be updated, but things have worked fairly stable, so we have stayed with it. It pulls up a window here that looks fairly typical, and for those of you who are used to MATLAB, it looks like a MATLAB window, and that's part of the point, is to have MATLAB and Simulink available, as well as having an extra GUI, which is sort of we call our blue GUI, which is sort of the RASP design GUI. RASP is an acronym that we've used for our FPAA family of chips for years, Reconfigurable Analog Signal Processor. And in one GUI, it contains a number of different options and things that you can use in this system and use for targeting this. There are many different key buttons here to look at. One of which you talk about is you can sort of pull up a new design, you can choose a design, you can open up a particular design, you can compile program, you can take data. There are different, each of these buttons have various key aspects to it. If I want to work with a particular board types, we have a few different types. I'm going to be using a 30A board. And I'm going to be using chip number 89, which is a board I use often personally. And then we can, from this, use multiple aspects. Now, typically when you pull down a VM, you might actually use update. We actually have two different forms of updating the tools, where you can either do an update or do a force reset. This is sort of the parts of the system that changes that change often are sitting in a GitLab repository, and so it can pull that up or completely reset and pull up the repository from scratch. There's some level of documentation for a number of different aspects, including the type of board infrastructure that we're looking at, number of utilities that are used often, and each of these are an interesting discussion unto themselves, as well as GUIs for additional advanced structures, say calibration, generating of macro blocks, and so forth. But in this part, I want to just go through an initial example that gets into this basic system. And that example I'm going to start with is to take a very simple structure where I'm going to compile an on-chip DAC to an ADC and then read it out. So, and of course there are parameters that are generated. Now, there's an arbitrary waveform generator. There's a measure voltage block, which is sort of the ADC block. There's a way I can run this from a simulation perspective as well, though I'm not going to show that in this case. It's kind of a trivial result. It also preloads a vector, and I can use a predefined vector, or I could create my own. I really don't want to create my own, so I'll use the one that's there, so I hit no. If I look at the arbitrary waveform generator, like most of these blocks, there's actually parameters I would look at. In this case, whether it's going to repeat, what the sample rate's going to be, what the variable name's going to be in this MATLAB-like workspace. Nothing's going to change, so I'll just cancel that. So once I've loaded that up from the example file, it's already chosen. So you can see the chosen part put right at that part of the structure, right in the middle there. And at that stage, now I can say, well, what would happen if I took the design and now compiled it? Well, I hit Compile Design, which allows me to compile it. It gives me a number of different outputs in these spots. And then simply at the end, when it's all done, it says it's completed and it's ready to program. At this point, I can now hit the Program Design button. And at that point, we can see what the program design is. Now, normally I wouldn't walk everyone through all the details of the design, but here it's kind of useful to see that we will end up having multiple aspects, one of which talking about there'll be an erasing, which is what you talk about, your tunneling and reverse tunneling. It'll then work on uploading the data, SRAM data, and then continue to program this. So we're running this in a verbose mode so you can see the details. You can also see that one of the other key things that was done here is that down here that you can see this going off where we've made sure to select the particular FPA board. If I didn't select the FPA board properly, then it would have trouble with the communication. And one of the biggest issues that we often find with all this tool set is not the FPA chips themselves, not the tool infrastructure itself, but rather some of the USB communication, which is always a questionable space for many people when they're building such designs. So which is one of the reasons we have a button here for resetting the communication. We also have additional sort of error messages and so forth to say if there's a communication problem so you're not surprised if there is an issue. Now a couple of the other buttons that are on here that are relevant, one of which is a view routing. The core of the tools uses VPR, and so you can actually look at the routing infrastructure that you might imagine using in that space. You also have the ability to load and program netlists, which netlist format here is in BLIF. And BLIF originally was a digital infrastructure, but we've decided to use it and extend it into the analog space. And so that actually allows me to do that, or I could do it purely from a switch list. Now, what I did after this was done programming is I decided to just take data. And take data is a function that allows me to take any SRAM or code that's loaded up, play it through the chip, and then run it back out. All of this is actually being done utilizing the processor on chip to make this work. This is simply doing a sweep where you can see this, the initial blue line is the inputs to the sweep, and the actual values that are measured out is actually through these green dots. And you might think this is a very simple measurement, just connecting two things really simple, a DAC and ADC, and it is. But remember, this is a DACs connected through to an ADC type device on the chip, which is actually compiling into the chip, which then runs through a use of the programming infrastructure onto an on-chip DAC and back into the SRAM memory through all of these data points. So in sequence, it allows you to see exactly how these tools work and the various pieces. In conclusion, I want to talk about the sort of open source FPAA tool. And the cool part of this tool is it enables, in a very graphical way, to have one open source tool that allows me to simulate, target, and design FPAs. And there's a whole bunch of material developed underneath it. The material has been developed heavily out of necessity originally, but then over time has become very, very important in terms of compiling structures in general, allowing us to talk about a whole range of applications going from sensors through computation, classification, and final computation, the sort of sensor to end result computing that we actually find very essential for a range of applications. Sensors could be acoustic sensors or a whole range of other kinds of sensor elements that you might imagine using here. And these can be deployed in many different forms, including Android devices. This was a tablet actually running and controlling an earlier FPA board. But there's a whole range of structures. And this really allows us to talk about a graphical design at the very top level of a whole bunch of pieces, maybe sensors, imagers, microphones, and all sorts of elements to classify it, and then talking about using that maybe as a wake-up device for other kind of computing. And this really allows us to enable a whole range of elements. And without the tools, none of this gets developed in any reasonable period of time.